So, welcome to the 15th lecture on module 1 on dynamics of ocean structures. In this particular lecture, we will talk about some examples on eigenvalue problems. So, we have made couple of examples in the last few lectures to make you to understand how to write equations of motion for a single degree and 2 degree, same concept for multi degree, how you can use principles of mechanics for finding out equivalent lateral stiffness matrix and how to get the frequency of vibration for an idealized single degree freedom system model. Now, if it is a double degree or multi degree, how will you actually get the omega? That is the problem what you are going to address today. But there is a very classical difficulty in writing equation of motion which we have experienced in the last few examples. Now, equation of motion can become simple if you choose the degrees of freedom as per the notion. It means the choice of degree of freedom will help you to make the equation of motion simpler. We will take an example where the degrees of freedom are not marked at the point where the mass is lumped. In all other earlier examples, we had seen the systems where the degrees of freedom are marked at the points where mass is lumped, but we very well know that the number of points lumped does not qualify for degree of freedom. Degree of freedom is related only to displacements. But fortunately or knowingly, we keep on lumping the mass at the points where degrees of freedom are marked. Therefore, mass matrix became always diagonal. It was easy for us to solve. Now, we will take an example where if the degrees of freedom are not marked at the point where the mass is lumped, or if the degree of freedom is marked at the point where the force is not applied, what happens to my equation of motion? What is the complexity? Okay? That is what we are going to talk about today. We will take an example like this. Let us say I have a system, maybe a pad or a deck resting on, let us say, 2 springs with 2 different stiffness, just for understanding purposes. Otherwise, you will not know, if you put both as k, you will actually not know which k I am handling in the equation. So, make it k1 and k2. System has got some Cg is the point. So, at this point, which is the mass center, I say my degrees of freedom in terms of force and rotation are marked. So, the force in the vertical axis is applied at the Cg point and the rotational motion is also applied, because you know spring has different stiffness. So, the pad will be keep on oscillating, it will create a motion or a rotation about this point Cg obviously. Therefore, we take that as the force P theta is the moment applied and this is the vertical force, whereas the degrees of freedom are marked at the point where stiffness is applied. Let us say this is my x1 and this is my x2, and of course, the mass is capital M with the total mass. Of course, the continuous mass can be m by L, and if the length is L, then obviously the total m by L into L will give you the capital mass. Let us even consider this L between the points where the degree of freedom is marked. Let us say this is L. Let us not take it to the end. Hypothetically, the points are at the end. I have given a deliberate space for you to see. Okay? They are actually at the ends. Okay? So, there are some important observations in this problem. The problem shows that the forces Pt and P theta are not applied at the point where the degrees of freedom are marked. That is the first observation. The second observation is the degrees of freedom are marked or selected in locations where stiffness is concentrated. So, from a first hand understanding, we will know that if you select the degrees of freedom at the point where the mass is lumped, you experienced the mass matrix to be diagonally dominant and the off diagonal elements were becoming 0. So, you can expect that in the stiffness matrix now. So, it is a very simple thumb rule. If your degrees of freedom align either with the lumped mass points or with the stiffness points, either of them will become off diagonal 0. Okay. In the earlier examples, you saw that the force is applied at the point where the degrees of freedom are measured. For example, a frame problem, we had x1 and x2, we had a lateral force. In the previous cases, we had x1, x2, we had a spring force. So, we always mark the forces where the degrees of freedom were marked or selected. But in this particular example, I deliberately violated this norm, saying that my forces will be applied at the CG where the degrees of freedom are not measured at CG. Deliberately a violation. Let us see what happens to this problem. If you have a problem of this nature, how will you solve? Before we solve this problem and write equation of motion, let us try to understand what is the practical applicability of this problem, where this problem applies. This has got two significant applications. One, it can be a foundation resting on a soil where the soil stiffness is modeled as a Winkler equivalent springs. Okay, that is one classical example of geotechnical application on dynamics. The second can be you want to isolate this deck from the substructure by some system. It means the vibration of the deck should not be transferred to the supporting system. It can be a seabed, it can be a pile, or it can be any other secondary or primary system on which the secondary system is resting. The idealized example of this could be a typewriter in olden days where people used to keep a pad below. When the typewriter is being used, the table does not vibrate. Or you would have noticed if the typewriter is kept directly on the table, you will see the legs of the table will get loosened very quickly because typewriter poses a lot of vibration in the vertical and horizontal axis. Okay. So, these are nothing but isolators, which is a very common practice in earthquake engineering. So, it has got very good applications practically in many examples. We will take an idealized model. Now, we all know at this moment clearly that it is a 2 degree freedom system model, a spring mass system. Mass is continuous of m by L nature, spring is available here. One can also convert it to an equivalent lateral stiffness of spring, or spring are in parallel, you can always find K equivalent, and you can always say the mass is lumped at this point and let the degree of freedom also be lumped here. You can convert this to equivalent single degree and solve. Okay. But I want to solve this as such as a 2 degree problem, and I want to write the equation of motion for this. Okay. So, let us first start with the difference of stiffness matrix. We know Kij is the stiffness coefficient. I want to find force at ith degree. I give unit displacement in the jth degree and I get the force, keeping all other degrees of freedom restrained. So, now this is a spring point which is actually hinged. So, there is no moment. So, this displacement which is x1 should be unity as per the derivation. So, I will get the force. Okay. So, the force will be applied vertically in the same direction because I want to apply this displacement, I must pull the spring up. Okay. I must pull the spring up to give this displacement, otherwise I cannot give this displacement x1 up, right. So, I should say this as my K11 row first column next, okay, and I must get this as my K21 row first column next. Remember, stiffness matrix is always derived column wise. Okay, you are giving displacement in the first degree, getting the force on all other degrees 1, 2, 3, 4 etc., but the second subscript will always remain 1 because you are giving unit displacement at the first degree. The first degree is here. Okay. So, obviously, K11 will be practically equal to my K1 because K1 is nothing but force per displacement. If the displacement is known to me as unity, I will get the force of the spring stiffness itself, is not it? And of course, the spring does not move at all, therefore, this is going to be 0. Similarly, I give unit displacement here and I want to pull the spring up, therefore, this is going to be K22 row first column next, and this is also going to be K12 row first column next. Stiffness matrix always derived column wise. So, the second column is now available to me, and for unit deflection or unit displacement in x2 direction, k2 is the stiffness, therefore, this will have be simply k2 and this will be 0, because this spring does not move at all, no extension caused to the spring. So, my stiffness matrix now is a 2 by 2 matrix. Why? Because there are 2 degrees of freedom. If there are n degrees of freedom, the stiffness matrix will be always n by n. Remember, the stiffness, mass, damping all will be always a square matrix. Okay. So, I can enter the values here k1, 0, 0, k2. You will experience immediately, since the degrees of freedom are marked at the points where stiffness is focused, the off diagonal elements are becoming 0, which was a practice earlier in mass matrix, because the point where the degrees of freedom marked were the points fortunately where the mass was lumped. Therefore, mass matrix became diagonal, now stiffness matrix become diagonal. So, one can immediately expect that the mass matrix, if we derive now for this problem, will not be, the off diagonal elements will not be 0, should not be rather 0. Okay, that is a cross check. So, let us say I want to derive the force vector. Now, why I am deriving a force vector? Because force is applied at a point different from that of degrees of freedom. Now, I want to know the contribution of Pt at x1 and x2, the contribution of P theta at x1 and x2 locations, they are different. If had the x1 x2 been located exactly at here and here, obviously x1 and x theta, then Pt and P theta will be simple vector, but in that case it is not so, because the contribution of Pt at x1 location, x2 location has got to be derived, they are not applied. Okay. Let us derive this. I apply Pt here. So, obviously by symmetry we know this is Pt by 2 and this is Pt by 2. I have taken a very simple example for you to understand. Okay. Similarly, apply P theta here. So, it is a clockwise moment, I must have an anti-clockwise couple, we already know this system of understanding, which will be P theta by L and P theta by L. Let me write it, L, where L is the length between the forces or the reaction. And remember, these reactions are actually offered by the springs. So, the spacing between the spring is L. Okay. So, L, hypothetically the springs are at the ends, but I have shown you to make it understand that they are located in the system like this. So, let us sum these two, because they are independent, let us sum these two and try to find out. So, the complete reaction will be minus of, okay, let us say my Pt is acting downward. So, I am putting it upward because I want x1 in the upward direction. I can write this as minus of Pt by 2 plus P theta by L. Okay. Similarly, x2 also I want in the upward direction, the force should be in the direction of that of x2, x2 is upward, therefore, I should say it is P theta by L minus Pt by 2. Okay. So, my force vector is like this, the P vector, which is the force vector, is minus Pt by 2 plus P theta by L, P theta by L minus Pt by 2. I have the force vector now. Okay. So, there is no damping matrix here, because there is no damping applied to the system here externally. So, damping matrix need not be derived. So, this is 2 by 1, okay, it is a vector, 2 rows and 1 column. Let us derive the mass matrix. We know that mass matrix is not going to have 0 off diagonal elements, they are called off diagonal, OFF, they are not half, okay, off diagonal elements, they will not be 0, because mass is continuous here, whereas the degrees of freedom are not measured at the point where the mass is supposed to be lumped, which is the mass center or center of mass or center of gravity. of the system. We will derive the mass matrix in the same fashion as the top stiffness. What we do is, instead of giving unit displacement, I give unit acceleration, same pattern. I am just following the same algorithm, but I do not give unit displacement for stiffness, I give unit acceleration for mass matrix. Okay. So, all are acting down, I have reactions, and this value which will act at the CG of this triangular loading will be m by L of L, which is considered as capital M. Okay. So, I will call this as small m, that is the mass matrix coefficient, as 2 1 1 1. The second subscript 1 shows that I have given unit acceleration at the first degree. The first subscript 1 and 2 shows these are the respective locations where mass need to be worked out, because these are the degrees of freedom marked in the problem. Okay. So, 1 1 and 2 1, I want to find these two from principle of statics very easily. I will take moment about this point. So, m 2 1 multiplied by the distance, which is L, should be equal to half, that is the triangular loading, base is L, height is unity, but it is m by L of L of unity, into 1/3 of L. So, this becomes m, this L goes away. So, my m 2 1 essentially becomes m by 6, half L, m by L into unity, this is unity, there is no L here, this is unity. So, that gives me the m value. So, this gives me the m value, okay, m by 6, half m by L of L into L minus m 2 1 so m by 3 into 1, sorry, m by L into L or into 1 of L. Let this L be here, this is the length, this 1 is the acceleration. Similarly, for the second node, you apply unit acceleration here, which is x 2 double dot is unity, and you get these values as m 1 2 and m 2 2. The second subscript indicates unit acceleration is at second degree, and I will get m 2 2 as m by 3 and m 1 2 as m by 6. So, my mass matrix will be m by 3, m by 6, m by 6, m by 3. So, you will see that the off diagonal elements are not 0, and however, the matrix is diagonally dominant, the values will be higher, okay, along the diagonal, along the leading diagonal, that is called leading diagonal of the matrix. The other one is called off diagonal of the matrix. So, I have now K matrix, I have now M, I have f of t. I can even write the equation of motion simply as M x double dot K x as f of t, which is this is 2 by 2, 2 by 1, 2 by 2, 2 by 1, 2 by 1. So, there is a total compatibility. So, the equation is written. Okay. Now, we know how to, we should know how to solve this. We have to now examine how to solve this equation of motion and how to find the essential characteristics of this function like omega and phi. because in the earlier examples being single degree or idealized single degree, we could find omega n very easily, either by finding out equivalent stiffness matrix or by a single stiffness and single mass we can find omega n. But in this case they are all full matrices. Okay. So, all the time you will not be able to idealize it a single degree, you must know how to solve for the natural frequency in the given system, what we now call as classical eigensolver problem. Okay. We will now enter into that. Now, any difficulty here? So, we have learned two things here. If the degrees of freedom are not selected carefully, you will end up in a system where the stiffness matrix can become 0, the mass matrix will have off diagonal elements. Okay. But one uniformity in all the problems is that the stiffness matrix and mass matrix and vector all will be symmetric and square more or less. But in offshore structures it is very interesting to know that off diagonal elements or the matrix stiffness and mass may become asymmetric also. Okay. So, one can easily argue a question that if the matrix remains all the time symmetric, then I can easily singularize this matrix and use only either upper triangular or lower triangular. I can save some time in solving this matrix, whereas in offshore structures the matrix that have to be solved is a full size, because you will have asymmetric elements in the matrix. So, where are those examples will come, because now in this case you see matrix whether K, not in this case, in other cases either K or M, they become more or less symmetric. Okay. But there should be some cases of structural forms of offshore structures which will invoke asymmetric non diagonal elements. So, what are those and why they become asymmetric? That is very interesting to know. Remember friends, only in offshore structures classical form of geometry asymmetric elements in mass matrix and stiffness matrix are available. In all the structural forms they will be always symmetric only. So, offshore structure therefore very special, okay, because we must know why they are asymmetric. I will come to that later in the second module. Now, let us understand simple problems first. So, now the question asked is, okay, now I have a mass k and c and f of t which are available to me, how do I get the natural frequency of vibration of this model? Okay, that is my problem, what we call classical eigensolver. This example which you discussed can also be discussed as a playfield problem, where a person sits and plays here, and the springs what you see here are the legs of the person who pushes and recoils. Okay, you must have used this game in your younger days. It is always advisable that you play with your brother or sister. If your father and you play, you will be always either down or he will be always up. Okay. So, the recoil is very high. It is a very simple model which is actually having application of dynamics, because the force is applied at this point, the pivot, whereas the reaction is given at a different point. Okay, that is a very interesting example what you can realize now at this age. So, all the games which has been practiced in India has got actually best engineering about 100 years back. That is why our social culture and our intelligence is appreciated all over the world, because we have applied engineering in even playing of games also. But the unfortunate part is they were not documented. Okay. So, we read them separately, therefore, we do not know how to integrate them. Okay. But when once they integrate, it becomes a patent of somebody else in abroad. We will take example 1 now, a classical eigensolver problem. We have already drawn this and derived these equations earlier yesterday in the last lecture. I will borrow the same equations, I will proceed further. So, this was a single bay 2-story problem with lumped mass at these points, which were 2m and m, and the height of the story was kept same, even this was kept as 2h, and the degrees of freedom were marked here as x1 and x2. We also had the mass matrix as 2m 0 0 m. Now, you will appreciate why I am writing 0 here, because mass is lumped at the same point where the degrees of freedom are marked. Stiffness matrix remains symmetric, EI and H being the property of the material and the members. and we say 24 EI by H cube as a multiplier out, we say this is 3 minus 1 1 1, is it so? Yeah. So, I simply say small k as 24 EI by H cube, that is my small k. Therefore, my capital K becomes 3k minus k minus k and k. Okay. You will again notice here that since stiffness is not the point where the degrees of freedom are marked, the stiffness matrix is in total and stiffness matrix is leading diagonal larger and it is symmetric. Okay, these are classical observations which you must keep on repeatedly observing when you keep on writing these matrices, so that you know that you are not making any mistake, and you will also know that carefully how you will select these degrees of freedom, so that they automatically get formed in a normal generation. Now, I have equation of motion which is mx double dot kx as 0 because there is no force applied to the system. Then one may ask a question, if there is no force, why displacement? We can also talk about free vibration. We also know that even the force not applied can give a displacement and the system will vibrate. Okay. So, I want to know the frequency of vibration or frequencies of vibration of the system. So, eigenvalue problem. Now, the first step is to find omega n, that is natural frequencies of the system. Now, one can ask a question, how many natural frequencies will be given in a system if the degrees of freedom is n? The degrees of freedom in a given system are n, you will have n number of natural frequencies. Of course, this n does not stand for the number, this stands for natural. Okay? This suffix n stands for natural. If you have n degrees of freedom here, you will have n omegas. Okay? The interesting part is all these n omegas will be unique. Okay? All will be unique. Let us see how. So, to find omega, the classical eigenvalue problem says take a determinant of an equation which is k minus omega square m and set it to 0. That is the mathematical implication of finding eigensolvers. So, let us do that here. Determinant of 3k minus omega square 2m, I am substituting the k and m value respectively in the respective slots. M is 0 here, therefore, it is minus k and k minus omega square m and set it to 0. Okay. So, 3k minus 2 omega square m of k minus omega square m minus k square is 0. So, 3k square minus 3 omega square km minus 2 omega square km plus 2 omega 4 m square minus k square is 0, implies 3k square, okay, 2k square minus 5 omega square km plus 2 omega 4 m square 0. Let omega square be x. So, 2k square minus 5 x km plus 2 x square m square is 0. 2 x square m square minus 5x km plus 2 k square is 0. So, can you find the roots x1 and x2? So, simple quadratic in x. Okay. So, simplify, you will get x1 comma x2 as phi plus or minus 3 km by 4m square. This multiplier and this multiplier is already there. Which implies that x1 can be 8 by 4 2 k by m and x2 can be 5 minus 3 2 by 4. So, k by 2 m. Okay. We already know that x is omega square. So, can I say this is omega 1 square and this is omega 2 square? Yes, already x is omega square. So, x1 is omega 1 square, x2 is omega 2 square. Is it not? So, these are the frequencies, because you know k and you know m. K is nothing but 24 E by h cube, m is m kg, which is given in the problem. You can easily find omega and omega 2, which we wanted. Okay. But unfortunately, the moment you start working on multi degrees, along with the frequency, one more pair will be generated, that is called mode shapes. So, mode shapes and frequencies are like husband and wife. So, once you have frequencies not frequency, if you have frequencies, it will automatically generate a pair which is mode shape. Mathematically, this is called eigen value and this is called eigen vector. Okay. So, the term itself very clearly tells me that this is a number, this is a corresponding vector to that number. That is why it is called eigen value and eigen vector. So, this is a vector corresponding to one number. It means every eigen value will have one vector. If there are two eigen values, there will be two vectors. Okay. So, the problem does not stop here. The moment you identify the husband, you have to identify the wife also, or you identify the wife, you must identify the husband, otherwise it is dangerous. Okay. So, we have to identify both of them parallelly. So, without one, the other has no value, especially in India we believe strongly this. Okay. Therefore, we have to identify this. Now, we identified either the husband or the wife, we really do not know, but we have to identify the corresponding counterpart. So, we want to find the eigenvectors also. Now, mathematically, to find eigenvector, the rule is A minus lambda x is set to 0. A is the matrix which is k minus omega square m. So, k minus omega square m matrix is what we call as the A matrix. Multiply this matrix with the vector which is phi vector, which is the eigen vector, set that to 0. So, let us see how we can do this. So, we already have this matrix with us. I have erased, but still you can help me in writing this matrix, which is going to be 3k minus 2m omega square minus k k minus omega square m. Multiplied by two vectors phi 1 phi 2, set it to 0. Okay, that is a generic equation. Now, remember in this equation you have the value of omega. So, if you really wanted to find the first vector, substitute omega 1 here. You want to find the second vector, substitute omega 2 here. Okay. So, I want to first substitute omega 1 and get phi 1. Phi 1 means not this phi 1, capital phi 1, first vector I want to get. So, each eigenvalue will have a unique corresponding vector. Okay? Let us do this. So, let me write down the values of omega 1 square and omega 2 square. Omega 1 square is 2k by m and omega 2 square is k by 2m. So, let us say omega 1 square, let still remember, be carefully notice this, I am saying it is only an assumption that omega 1 value is equal to 2k by m. One can ask me a question, amongst these two frequencies which is named as fundamental frequency or which is the first frequency in the first mode shape. Unless otherwise you know the values of both, you cannot find, because these are nothing but the roots of the quadratic equation. Which root is cutting the x axis first, we really do not know, because there are no algebraic value, numeric values for these numbers. Okay, let us first find the numeric value, then we will say which is omega 1, which is omega 2. This omega 1 does not mean this is the first frequency. I am calling this omega 1 because this is going to correspond to my so called omega 1 in my problem. Ultimately, after I get both omega 1, omega 2, then I must consolidate and say which is the fundamental frequency with the next frequency, because now I have no numeric value for this. Depending upon the value of k and m, you know these values can be different. Okay? Therefore, we cannot comment that. So, do not get confused that when I write omega 1 this is the first frequency or fundamental frequency, not like that, we really do not know that, we have to estimate that. In this problem deliberately I have taken this as omega 1, but it will not be omega 1, I have deliberately taken like this. Okay? So, let us try to find out this. So, 3k, let omega 1 square be substituted. So, 3k minus 2m of omega 1 square is already 2k by m minus k minus 2k by m of phi 1 phi 2 is set to 0. So, if I simplify this, m goes away, 4k, 3k minus 4k is minus k, this goes away minus k, okay, of phi 1 phi 2 is set to 0. Let me expand this, row and column are multiplied, we know how to multiply them, you can see the compatibility, okay, they are perfectly compatible, right. So, minus k of phi 1 minus k of phi 2 is 0, minus k of phi 1 minus k of phi 2 is 0. Both equations are same. Now, there is a mathematical instability in solving this problem. I have two unknowns phi 1 and phi 2, I must get two equations, I am getting two equations, but both of them are same. How do I solve this? Okay. In this case, please understand phi 1 and phi 2 are relative values, they are not absolute. So, I will assume one, get the other in proportion of the one. Okay. That is why they are called relative numbers. Okay. So, I will take away this, I will just retain only this part. So, this implies that minus phi 1 is phi 2, any equation pick up, this implies that minus phi 1 is phi 2. Okay. So, if phi 2 is phi 2, phi 1 is minus of phi 2, can I say this? If phi 2 is phi 2, phi 1 is minus of phi 2. Okay? I got the value now. Let us say let phi 2 be 1, phi 1 will be minus 1, proportionate, is it not? So, my vector is very simple now. For this the corresponding vector is 1 and minus 1, no, this is 1 and this is minus 1. Phi 1 is negative of phi 2. One can ask a very serious question here. So, you have taken phi 2 as phi 2, say let phi 1 be phi 1, phi 2 is minus phi 1, my vector is going to be 1 minus 1, is it not same as this, is it correct? Both are all right, they are proportional only, okay, both are all right. So, if you are happy on Mondays this way, you do it, if you are happy on Tuesdays, do it this way, so it does not matter. So, we got the first vector corresponding to the first value. Now, I want to find the same procedure for the second set. So, k minus omega square m multiplied with phi should set to 0, and let us do this matrix again. So, 3k minus 2 omega square m minus k minus omega square m. I substitute 2 here, multiply this with the vector phi 1 and phi 2, set it to 0. Remember, please note, this phi 1 is nothing to do with this phi 1. This is the second vector. This is where the confusion will start. People will start substituting these values here, they are messing up. Okay? It is not. This is something different vector, because remember, that is why I said this is an husband of this wife. He cannot be an husband of this wife. It is very simple to understand physically like this, provided it is applicable only to India, I think, but still does not matter. Okay, let us say phi 1 and phi 2. So, can you quickly find out phi 1 and phi 2? So, you have to give me like this, which is 1 and which is 2, because I am confused which is 1. Yeah. Okay. Now, let us try to find out which is my fundamental frequency. There are two ways of finding out this. Please understand this very carefully. This is the point where very intrinsic discussion and understanding is required. One way of finding out this is, you substitute the value of k and m, if you know, get the numeric value. Now, k I have 24 E I by h cube, I will know the value of E, Young's modulus, I know the value of I, the section is known to me, I know the dimension, I can find, I know m, I can find and can get the numerical answer, can compare. But the easiest and correct way to find out is this: when the vectors have got both positive representation, there is no zero crossing. Let us plot this. This is my structural system. Eigenvectors are displacements relative to each other. Why displacements? x1, x2 are actually displacements. Okay. Now, I say here from this vector, if the first mass is displaced by 1 times, the second mass is displaced by 2 times as per this vector. So, the deflected shape of the mass does not cross equilibrium at any stage. This is called the first mode. On the other hand, to be as a thumb rule, first mode will have all positive or all negative displacements. There should be no crossing. Now, plot the second one. If the first mode is negative, the second mode is positive. So, I have a structure like this. It has crossed. This is second mode. Now, one can ask me a question, sir, let us plot the third mode. In this case, it is not applicable, you will have 2 crossing. Can I find out something related to this? If your mode is nth number, you will have n minus 1 crossing. If the mode is the first number, there is no crossing, because 1 minus 1 becomes 0. So, now, since this is the first mode, the corresponding wife is the first frequency. Okay? The corresponding eigenvalue is the first frequency, which is this. So, I can call this as fundamental frequency even without knowing the values of k and m. That is very, very important to understand. Okay? Characterizing the fundamental frequency should be based on the deflected shape or the mode shape of the system, not on the numeric value alone. Okay. Now, let us see if I substitute numeric value, what happens. Let us pick up this 24 E I by h cube by m, and this value is 2 into 24 E I by h cube by m. Okay. If I say EABH cube m is a value of 1000, 15,000, any number, this value will be always lower than this, okay, which implies the same meaning, it will be the first mode. Okay. So, do not try to compare numeric answers and then conclude the first mode or the fundamental frequency. Fundamental frequency is the first frequency at which the system will have no crossing from the equilibrium position. Okay. So, it is easy for us to identify. So, if I have n frequencies in a given system, I will have n degrees of freedom, I have n frequencies, okay, and all matrices, mass, stiffness, everything will be a square of size n by n. Let us quickly spend about 5 more minutes to give you a self learning assignment which I want you to solve. So, there are some self assessment questions, please pay attention to this and try to solve them. A damper offers resistance to the value of 0.05 Newton at a constant velocity of 0.04 meter per second. You can note down these values and try to solve them. The damper is used with stiffness of 9 Newton per meter. Determine the damping ratio and the frequency of the system when the mass of the system is 0.1 kg. Of course, a model study. Okay. Anyway, the questions will be available posted in NPTEL, you can see them later, but try to understand, write down the knowns and unknowns clearly, and are you capable of solving this problem. The second question is on a vibrating system which is defined by the following parameters: mass is given, stiffness is given, damping coefficient or constant is known. I want to find the damping factor zeta, the natural frequency, damped vibration omega d, which we already solved a similar problem in the class. One can easily solve this problem. The third question is again a mass of 7 kg is kept on 2 slabs of isolators. There are 2 slabs of isolators, a mass of 7 kg is kept. One is a synthetic rubber, stiffness is so much, damping coefficient so much. The second is a fibrous felt, stiffness so much, damping so much. Okay. We are trying to work out a relative displacement with these two. So, if the assembly is vibrated in vertical direction actuating the series isolators, determine the damped and undamped frequencies. A vibrating system having a mass of 1 kg suspended by a spring of stiffness 10 or 1000 Newton per meter. It is put in harmonic excitation of amplitude 10 newtons. Assuming viscous damping, find out resonance frequency is a forced vibration problem. Resonance frequency, amplitude resonance, frequency correspond to peak amplitude and the damped frequency omega d if C is known to you. The fifth problem, body of mass 70 kg suspended from a spring which deflects 2 centimeter under the given load. So, the static deflection is known to me. So, initial displacement x naught is now given to me. It is subjected to damping whose value is tuned to be 0.23 times of that are the value of the critical damping. So, critical damping you must first find out. Find the natural frequency of undamped and damped vibration and the ratio of successive amplitudes from the logarithmic decrement equation. If the body is now subjected to a periodic disturbing force of 700 newtons and of a frequency equal to 0.78 times of omega d, then now find the amplitude of forced vibration and the phase difference between the respective disturbing forces. So, try to solve this problem and understand the answers of it. We will not solve this problem here, it is a self assessment you must solve. Okay. So, kindly do not pose any request of giving the solutions for this in NPTEL, we will not give this, actually it will remain as unsolved until the exam is done. Okay.